Okay, let's start. Okay, this is going to be 2020 May-June paper. Okay, it's 1 hour 15 minutes. Let's actually try to finish this in 1 hour today. Okay, I will just go through very fast. Okay, so here we have gallium, okay, an element in group 13, and you have, okay, you are trying to analyze this using mass spectrometer. Okay, these are the abundance. So the mass spectrum is shown, and then we need to actually explain what is relative atomic mass. So when you want to explain about relative atomic mass, always remember it's actually average mass. It's very important to actually mention about average. It's an average mass of one atom compared to 1/12 of the mass of another one atom of carbon 12. Okay, so the part that we will actually mistaken over here or something will be missing is more towards this part, okay, the average. And then students tend to actually forget about this carbon 12. I think 1/12, I think quite common. I think students tend to actually write that 1/12. Okay, but the part that will be missing most of the time will be average and then the carbon 12. Okay, take note of that. Calculate the relative atomic mass of gallium in this sample. So you have, okay, a total of 100% over here. So what you need to do, you just take the 60.11 over 100 times 69. Okay, you just have this calculation, 39.89%. Okay, you times with 71. And when you calculate, okay, when you calculate, just use your calculator, you will get 69.80. We want the answer in 3 significant figures. Okay, if you give 69.8, should be okay. Okay, so in this case, if you want to give more, it's also okay. Yeah, 69.80 will be the answer. Okay, just to save time, okay, I have done this earlier for you. I'm very sure you can actually do this, all this. Now, complete the table which describes a gaseous atom of gallium. Now, gallium, okay, they have given you the 71. Always remember when you have X, okay, the A, okay, that is at the bottom, and then you have the Z over there at the top. Now, A at the bottom will always represent your proton number or your atomic number. Okay, forget about how it is represented in the periodic table. We don't bother about that. Okay, but whenever you actually have in form of writing, the top part will always represent the nucleon number. So if this one, the nucleon number over here is going to be 71, which is your mass number. Okay, mass number. So they ask what is nucleon number. No need to refer to your periodic table. The nucleon number is 71. Okay, total number of electrons in lowest energy level. I think this one no need to even actually look at your periodic table yet also. Okay, because I think when we fill up any electrons in any atom, okay, we always fill up, okay, from the lowest energy level followed by the highest energy level. Okay, so when you fill up like that, okay, what is going to happen is, okay, we will have 1s2 and then followed by the rest. Okay, so the lowest energy level, okay, is going to be 1s. So therefore the energy, the number of electron in the lowest energy level will be always going to be 2. Okay, that's going to be the number of electrons. Now, type of orbital that contains the electron in the highest energy level, yes, you need to actually refer to your periodic table for this. Okay, why? Okay, if you look at your periodic table, I actually took some portion of the periodic table. Okay, and I'm interested with gallium. Okay, this is gallium. But when I look over here, okay, you can actually separate, okay, your periodic table into 3 parts. Okay, which is going to be the S. Okay, it's not visible over here. Some parts of the D is over here, and then P, SDP. Now, when you have SDP, it means that, okay, I think I told you last time how to actually complete the electronic structure in a faster way or something like that. Okay, if you look over there, this part will be 3D. Okay, it means 3D what? If you have, okay, 10, okay, so then it's going to be 4s2, 3d8, and so on. So when it comes to zinc, it's going to be 4s2, 3d10. Okay. But the moment when they come to here, okay, gallium, then you will have 4p. Okay, this one I told you to start memorize, okay, where I told you that before 3D, then you start with 4s, 3D, and then this one will be 4p. Okay, so this one will be 3p, okay, and 2p, and so on. Okay, this one will be 5p. So here we are talking about, okay, the p, everything that comes under p block, okay, that is going to be going to end with p. So here the highest energy level, okay, because gallium is in the p block, so the highest energy level is going to be p. To be exact, what is that? So to be exact is 4p1. Okay, 4p1. So it ends with 4p1. So how about germanium then? So germanium ends with 4p2. Okay, and then the rest, okay, I just took up to here only. Okay, so do remember how to actually refer to your periodic table for this. Okay, lowest energy, highest energy level. Do remember when you want to remove the electrons, you also remove from the lowest energy level. Okay, so I think there is some kind of contradiction over there. How do we remove the electron from the lowest energy level? So we are talking about different energy levels over here. So if, for example, if you have a transition element over here, like for example, zinc, for you have, okay, zinc is 4s2, okay, and then we have 3d10. Now, if I want to actually remove the electrons from zinc, okay, the first electron that I remove must be from the lowest energy level, which is going to be from 4s. You remove from 4s first, okay, before removing it from 3d. Okay, there is some sort of contradiction over there. Okay, always remember when you fill in the electron, you fill in 4s. When you remove from 4s also. Okay, so next, okay, we will go to D. When gallium is heated, okay, in excess chlorine, okay, chloride, gallium trichloride is made. Okay, gallium, you see here, is in the same group as aluminium. It means it's actually in group 13. Okay, 3 valence electrons. So draw the shape and suggest the bond angle. I think very easy. Ga. Okay, and then you have Cl. They say draw shape. No need to actually draw the cross dot diagram. Just draw a normal shape. Okay, this one 3 valence electrons. So they have 3 bonding pair. Okay, therefore, okay, the bond angle suggests the bond angle is going to be 120 degrees. That's going to be the bond angle. Okay, so let's actually find out what is the shape of the molecule then. The name. Easton, can you tell us what is the name of the shape? Hurry up. Lavi, can you give me the name of the shape?
Tetrahedron.
No. Come on, Lavi. Prelim next week.
Aduh.
Okay. Trigonal planar. Yeah. So tetrahedra is 4 bonding pair. Okay. So this one is trigonal planar with 120 degrees. Yeah. So here, okay, gallium oxide, okay, and aluminium oxide react in the same way with ACl and with sodium hydroxide. So basically, they're telling that aluminium oxide and gallium oxide, they react in the same way. And I know that aluminium oxide is amphoteric. Okay, Charlton, can you tell me, okay, what is amphoteric, Charlton?
Can react with acid and base.
Yes, they can react with acid and base. So take note of this. Okay. So this one, okay, there is a reaction with acid and base. Therefore, okay, we see that when you are going to do reaction, when you are writing the reaction between this ACl and NaOH, I think it's a very good practice if you can actually know or write first what is going to be the reaction between aluminium oxide and the acid. Okay, this one, if you want to check, you can check in your textbook, page 156. But I have actually written down over here, okay, when aluminium oxide reacts with any acid, in this case, is going to be sulfuric acid. It gives you the aluminium sulfate, which is going to be the salt and water. So if I have gallium oxide, okay, the same reaction is going to happen. HCl, okay, I know that this is going to be group 3. So of course, I'm going to get Ga3 plus. So it means Ga3 plus Cl minus. So GaCl3, okay, plus H2O. So what is left over here is just, we need to just balance it. Okay, I have 2 Ga, so I just put 2 there. And that makes total Cl to be 6. Okay, so I just put 6 over here. Okay, when I make 6, okay, I'm going to have 6 hydrogen, 3 oxygen, so I just put 3 there. Everything's balanced. Okay, so you need to balance this. Now, the second equation is reaction with gallium oxide, okay, with sodium hydroxide. Okay, I think this one is much more like complicated a bit. I think I want you to memorize this, yeah, what will happen. Okay, for example, if you have aluminium oxide reacting with sodium hydroxide, okay, it is important to include water. Okay, they will actually include with water. They will give you sodium, okay, and then the AlOH4 minus, it means Na plus AlOH4 minus will join together. Okay, so in this case, okay, if we try to replicate the same thing over here, it will look like this: Ga2O3. I'm going to react with sodium hydroxide. It means I need to actually have reaction with water as well. And it is going to give me, okay, forget about the numbers, the 2 and so on. Okay, first write down. So it will give me Na. It's supposed to give me AlOH4 minus. So now it will give you GaOH4, okay, minus. So when they are together, you are going to have Na together. Okay. So now, okay, we need to actually balance this, okay, because we have Ga2 there. Okay, of course, I need to actually put 2 there. And because I have 2 Na on my right hand side, I need to put another 2 here. Okay, then the rest is going to be trying to balance the hydrogen. Okay, hydrogen is 8 on the right hand side. I need to actually make sure I have 8 over here. So I have 2 here. So I just need another 6. So I put 3 there. Okay, now it's balanced. So this one you can only do, okay, if you know about this. If you don't know, then easily you will lose the mark. Okay, do remember that's the reason. Very rarely they actually give you balancing equation with 2 marks. Okay, very, very rare. So this is actually really testing you on the ability of you to remember what is going to happen and ability to change, okay, from Al to become Ga. So basically, there's nothing different over here. The only thing that is different is changing Al into Ga. That's it. Okay. So in order to do that, and also they give you mark for balancing. So of course, I don't encourage you to memorize how to balance. Okay. I will encourage you to memorize what will react. Like for example, sodium hydroxide. Yeah, do remember on your left hand side, you must have water. Okay, let's actually move on. Now, nitric acid can be made in a 3-stage process. Okay, 15 minutes for the first question. So we are still slow, yeah. Now, nitric acid can be made in a 3-stage process. Okay, you have all these stages and so on. Stage 1, okay, they say that, okay, let's straight away answer the question. Ammonia is oxidized by oxygen. So write down NH3 oxidized by oxygen. Okay, to form nitrogen monoxide. So NO and water. Okay, the reaction is carried out, blah, blah, blah. Okay, we don't care so much for now. Okay, but do remember, okay, maybe later we might actually consider this. Okay, but now they just want you to write an equation. Equation is written, but you will not get the full mark if it is not balanced. Okay, so make sure it is balanced. Okay, so here is going to be NH3, okay, NO. So first, what we need to do, I think you still need to balance the hydrogen. So the way that we balance the hydrogen is by maybe just put 2 there. Okay, so when you put 2, the hydrogen will become 6, nitrogen will become 2. So I need to put 2 here. Okay, how to make hydrogen to become 6? By putting 3 here. So the last one that you balance is going to be the oxygen. So on the right hand side, I have 2 oxygen plus 3 oxygen. So that will give me 5 oxygen, and I know if I put 5 over 2, everything is balanced. But I strongly advise you, okay, do not actually leave your answer in form of fraction. So times everything by 2, you're supposed to get this particular answer. So do not, okay, leave your answer in fraction. This is strongly my advice. Okay, don't leave your answer in fraction unless it is actually really required when it comes to enthalpy or to show enthalpy. Then you leave it in fractions. But as much as possible, when enthalpy is not involved, okay, please don't use fraction. Yeah. Now, draw a dot and cross diagram to show the arrangement. So I have actually started earlier. So here I just draw, okay, so you have the circles and so on. In a molecule of ammonia, ammonia is group 15, 5 valence electron. So they are going to share with 3 atoms of hydrogen. So ammonia, they share 3. So again, from hydrogen, you will get the X, okay. And do remember ammonia has 5 valence electrons, so put the remaining 2 electrons outside. Okay, so draw cross and dot diagram is already 1 mark done. Yeah. Now in the boxes, give the oxidation numbers, okay, of nitrogen. We need to calculate. Okay, and then how to calculate? I think whenever you have a neutral molecule, we can calculate easily. But whenever it is going to be something like HNO3, I will strongly advise you to change it into ions, H plus NO3 minus. So you just take the NO3 minus and then just keep it NO. So we will calculate now. Okay, if let's say nitrogen is X, okay, so I just put X plus, okay, 2 times negative 2. By now you should know oxygen is always negative 2. So X equals to positive 4. Okay, so here the answer will be positive 4. Ignore the 3, ignore the 2, all this will not be, is useless now. Yeah. So here is X plus 3 times negative 2 equals to, don't forget, it's going to be negative 1. So X equals to negative 1, bring it that side, plus 6. So you will get positive 5. Some students forget, okay, to put positive 5. Maybe I tend to actually put positive quite often. Okay, so I also forget to inform you, okay, or emphasize, okay, do not put 5 alone. Please put the plus, okay, please put the plus. Okay, don't actually go and put 5 plus also. That is wrong as well. Okay, we always use copper 2 plus, something like that. Okay, when some students do write copper plus 2. No, it doesn't work that way. Okay, so it's copper 2 plus when you write, okay, in form of ion. Okay, but when you calculate and then you want to write the oxidation number and so on, so the plus, okay, will come in front. Okay, so this one is going to be X minus 2 equals to 0, X equals to plus 2. So write down plus 2. Now, explain, okay, why the reaction in stage 3 is described as disproportionation reaction, but there is a catch to it. Okay, they say include reference to transfer of electrons. It means they don't want to hear you guys to talk about oxidation number. Okay, they want you to straight away talk about, okay, reference to electrons. Okay, so when you look at this one, okay, we know, okay, from plus 4 to become plus 5, I know this is going to be oxidized. Okay, increase in oxidation number. Okay, when I change from here to here, I know this is reduced, okay, because it's going to be decrease in oxidation number. Okay, now when something is oxidized, okay, it means that you lose electron or gain electron. Lavi. Oil rig,
This
oxidized is loss of electron. Okay, even you can actually see from the, okay, you can even see from the number, yeah. How to get plus 4 to become plus 5, okay? It means you must lose 1 electron, lose 1 negative 1, yeah? So you lose 1 electron, okay, lost 1 electron, okay? This one, you get reduced because you add, okay, how many electron? Okay, you are adding, okay, gain of electron. So you are adding from 4 to become 2, it means you're adding plus negative 2. Okay, it means that every 1 electron is negative 1. Okay, it means you are adding how many electrons? You are adding 2 electrons. So here, when you actually describe this, okay, you need to actually mention, okay, NO2, okay, when it is changing to become, okay, you write it in your own sentence, okay, to become HNO3, okay, we call it, okay, this reaction as, okay, oxidation. Why? Okay, because, okay, because one electron is lost, okay, is lost from NO2, okay. So you just put one electron is lost from NO2, or you can say one electron is transferred. Okay, if you want to change it a little bit, one electron is transferred, okay, from NO2, okay, to HNO3. Done. The second one is, okay, you need to actually mention about the NO2 to change into NO. We call it reduction because two electrons are gained. Okay, two electrons are gained from NO2 to where? To NO. Okay, please actually write down all this. Okay, the important key points will be the electrons. Okay, we don't want to actually refer to the oxidation number.
Sir,
Yeah,
I go toilet.
yeah. Now let's move on. Okay, the release of nitrogen monoxide causes atmospheric pollution. I think every single time when you see this kind of question, I think it's getting like similar. How come it's the same thing over and over? Yes, they do actually ask the same thing over and over. State and explain the effect of nitrogen monoxide in contact of moist air. Okay, nitrogen monoxide, okay, when they come into contact with moist air, okay, they will actually give you, okay, an acidic solution. Okay, so this one they will give, okay, nitric acid. They will form nitric acid. Okay, so when they form nitric acid, okay, so the effect of this, it will cause, okay, it will cause acid rain. Okay, and will cause acid rain. If they ask more, then the acid rain will destroy plants. Okay, the acid rain will actually decrease the pH of the soil. Okay, so it will decrease the it will spoil the plants. Okay, it will kill all the aquatic animals because it will change the pH of the river. Okay, what else? I think it will also destroy buildings. Okay, that has a lot of metal structure. Okay, so please actually go through that. Yeah. So do remember nitrogen monoxide, okay, is going to be anything that is non-metal oxide, the one on the right-hand side of the periodic table, okay, they are going to be acidic oxides, okay, acidic oxides. Now, nitric acid made in stage 3 can be reacted with ammonia to form ammonium nitrate, okay. So calculate the volume of nitrogen dioxide measured at room temperature and pressure required to make 40 tons of ammonium nitrate. So this is ammonium nitrate. They want to make 40 tons of this. So first of all, I need to find the number of moles of ammonium nitrate. So I change 40 tons, okay, is 40 times 10 to the power of 3 kilogram. I still need to change it into grams. So I times with another 10 to the power of 3. In total, I will get 4 times 10 to the power of 7 gram. And what I need to do, I need to change into number of moles. So I put this divide by MR of ammonium nitrate. And if you calculate, okay, you will get 500,000 mole. Okay. Once you get that, okay, it means that now in order to get this 500,000, okay, 500,000, I need, okay, how many moles of nitric acid, because I need to relate to this equation. Okay, so how to relate? The only thing that you can relate is HNO3. Yeah, so how do I relate? Okay, 1 mole equals to 1 mole. Okay, the number of moles that is the same. So the ratio is 1 to 1. Okay, so if this one is 500,000, this one is also going to be 500,000. Now, one of the common mistake the students will make is when they actually try to relate over here, or they saw, oh, 1, this is 2, and then they go and times by 2. This is totally wrong. Okay, do remember the ratio that you have is going to actually work for that particular equation only. Okay, it means the ratio that you have will only work for this particular equation. It will not work when you actually take this and you go there, you are going to times by 2. No, it means that if you have 500,000, this is 500,000. Okay, this is 500,000. So what you need to do now, this 500,000 in this particular equation will represent the ratio of 2. If you are looking for NO2, okay, if you want to find out what is NO2, you need to follow this ratio now. 2 represents 500,000, 1 represents 250,000. If I want 3, it means it will give me 750,000. Now that is number of moles. Okay, and I know, okay, 1 mole, okay, it will give you 24 dm cube. So you just times, okay, 24 times 750,000, and you will get this answer. Okay, this is the volume. You can write this answer, or if you want to write 1.80, okay, so it means 3 significant figures: 1, 2, 3, 4, 5, 6, 7 times 10 to the power of 7 dm cube. Okay, please do that as well. Okay, so this one, okay, I think this one, the previous, I think from the same paper, same year, okay, in the paper 2019, 1 year before, okay, the previous taking, we actually have, okay, 1 use of ammonium nitrate. Okay, so here they ask also, what is 1 use of ammonium nitrate? So Janice, what is the use?
Fertilizers.
Very good. Okay, easy 1 mark. Yeah, fertilizers. Now, so number 3. Okay, again, we finish another question in 15 minutes. Now, sucrose reacts with water to form glucose and fructose in reaction A. Okay, so it means they react and then give you this. Okay, this one suggests a name for this type of reaction. Do remember, whenever you use water to break any kind of bond, okay, this is going to be named as what, Justin? What type of mechanism?
Condensation.
No. Condensation is you are trying to actually take out water. Okay, this one you are using water to break something. Water is hydro. Breaking is lysis. So this one is called hydrolysis. So this is not condensation. Okay, hydrolysis, using water to break something. Okay, condensation means you are going to get the product as water. Okay, product will be water. So take note of this. Okay, this is going to be very important. Explain in detail why glucose and fructose are pair of structural isomers. Okay, your answer should refer specifically to these 2 molecules. It means I need to really focus on this and tell that these 2 are structural isomers. So I think the only way to actually show they are structural isomers will be structural isomers. I think they should have the same molecular formula. Okay, so I need to actually find out the molecular formula. They have the same molecular formula but different structure. Okay, so the structure can be, I think what I can see over here is I see that the double bond, okay, here this is like, looks like aldehyde. Okay, but here the double bond, they actually came from this carbon went to the second carbon over here. Okay, so this one, I think the double bond, C double bond went to carbon number 2. Okay, this is what I can see from the difference directly over here. Okay, so what I can do is I find out for glucose what is going to be the molecular formula, fructose how many what is the molecular formula. In order to do that, just calculate. So this is 1, 2, 3, 4, 5, 6. So C6, how many hydrogen? Okay, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So H12, how many O? 1, 2, 3, 4, 5, 6. Okay. So if they say no need to waste time, they already say it's actually structural formula. I know that they have same molecular formula. It means C6H12O6. So to save time, what I will do, I'll just say, okay, both okay, glucose and fructose have the same molecular formula. Make sure you mention. If you don't mention, you will lose marks specifically here. So C6H12O6. Okay, but okay, glucose have okay carbonyl group or C double bond O at first carbon. Or you can say rather than putting first carbon, it means double bond O at first carbon. And double bond O is at or is in second carbon in sucrose, in fructose. Okay, that is going to be in fructose. Yeah, reaction A, okay, occurs faster in the presence of enzyme. Okay, they so what is actually reaction A? Let's actually see. They say this reaction A, if you have enzyme, then it's going to be faster. In this case, they didn't say it's going to be in enzyme. If you have enzyme, it's going to be faster. Then they say if it is faster, okay, then it's actually going to be reaction B, which is going to be with the enzyme. Okay, with the enzyme is going to be reaction B. Now, activation energy for reaction B is plus 29. So predict a value for the activation energy of reaction A. It means reaction A is without the enzyme. So if I predict, maybe I'll predict something higher than 29. Okay, maybe I'll predict 40 kilojoule per mole. Any value that is higher than 29, but do not forget the plus. Okay, plus 40 kilojoule per mole or plus 35 kilojoule per mole. Don't go and put near to that like 30 kilojoule per mole. No, I think try to be higher a bit. Yeah. Now the enthalpy change for the reaction A, okay, is negative 14. Predict the value for the enthalpy change. I think during whenever you use catalase or whenever you are using enzyme, okay, the enthalpy change, they don't change. Like for example, if you have something like this, it means when you have enzyme or something, what will happen? The activation energy only will decrease, but they will actually end start from A and at B. So your enthalpy change will still remain the same. Okay, nothing changed over there. So here we are going to have 14 kilojoule per mole also. Nothing changed. Okay, nothing changes. So here sketch a label energy level diagram. So I do not know whether how to sketch, because I know one is going to be like this, another one is going to be like this. Which one I should choose, whether exothermic or endothermic? Then refer to the some of the information given earlier. They say it's actually negative 14. Okay, if negative 14 is definitely going to be exothermic. So you try to draw this. Okay, so here, okay, if you label, okay, you just take this one, okay, and then you just draw like this, and then okay, you just put like this. Okay, so this is going to be, okay, from here to here, this is going to be negative 14 kilojoule per mole. And this one from here, okay, from the reactant to the top, okay, the activation energy is going to be plus 29. Hold on for a Baby. No, no, no. Don't cry, don't cry. Okay, let's continue. So here, sketch a label energy diagram. Okay, use relevant value. So please actually label. Yeah. So this one is going to be EA, your activation energy. Sometimes maybe if they don't understand, so just I think we just write down activation energy. Sorry, activation energy. And this one is going to be delta H, your enthalpy. Okay, so you can actually label. Yeah, please label. Now, so the next question over here, okay, is going to be 1 gram of sucrose completely combusted. Okay, the heat energy produced is used to increase the temperature. So do remember, it's an exothermic reaction. Okay, I think one of the mistake that students actually always make is when they say, oh, there is increase in temperature, final answer, they forget to actually put it as negative. Yeah, so it's going to be exothermic. Okay, when I calculate, okay, this one no need to change it to Kelvin, yeah, because this one difference in temperature. Okay, so it's supposed to be 225 plus 273, and then 40.7 plus 273. When you deduct, okay, you find the difference, this one will cancel off. Okay, so here, okay, I have found out that delta T is going to be 15.7, 40.7 minus 25. Okay, and then okay, delta C, okay, from the data booklet you'll get 4.18. 4.18 is the heat capacity for water. It means when you actually use this value M, it must be in gram. Okay, it must be in gram. But sometimes we are not sure whether which one should we use. Should we use 250 gram of water, or should I use 1 gram of sucrose? Or should I use both of them added together, 250 and 1? Is it going to be 251? I think to answer this question, I think it's very simple. Okay, because you are using the heat capacity of water, you take only the water, the mass of water. Okay, so the mass of water is 250. Okay, you put 250, you get this. Okay, it means all the heat, okay, when you heat up the sucrose, it's all going to be transferred to the water. Okay, so what I need to do is I still need to find the number of moles of sucrose, okay, that I use. So I will actually calculate and I get, okay, 1 over 342 moles, okay, of sucrose. Okay, but before that, okay, please, maybe I missed this, okay. Enthalpy change of combustion. Enthalpy change of combustion is when 1 mole, okay, they say sucrose, yeah. So 1 mole of sucrose completely burns with oxygen or completely reacts with oxygen, okay, under standard conditions. So they want 1 mole of sucrose, okay, and completely reacts with oxygen, okay, they want this. Okay, please take note. Now, the next, okay, if you want to actually calculate, they say when you want to calculate the enthalpy change, okay, of combustion, okay, we need to find for 1 mole because it's for 1 mole. Okay, but just now, okay, what this value is for 1 over 342 moles. Okay, so what we need to do, find out for 1 mole, it means 1 mole is this value. I need to times by 342. Okay, and when you times, you will get your answer in joule. Yeah, take note, you will get your answer in joule. Okay, and then here they want in kilojoule. You need to divide by 1000. Okay, probably you will get 5610000 joule per mole. So when you actually write your answer over here, you need to change it into kilojoule, 5610. Okay, divide by 1000. But do not forget this negative. Okay, do not forget. In the past, okay, they actually used to give like this. Okay, they give you like this. Okay, then they say magnitude. Okay, magnitude, and then symbol, then magnitude over here. So we know, okay, we know that you need to actually give symbol plus or negative, and then the value. Okay, so we know, but this one, okay, it's not clear. Okay, and do remember this is a recent paper, so they didn't give over here. So most likely when you it comes for your sitting as well, okay, they will not give you anymore. Okay, so take note of that. Okay, no negative, you will miss. Even though everything is correct, you will only get 2 marks. Take note of that. Now number 4, okay, an unlabeled bottle contains a straight chain halogenoalkane. Okay, the molecular formula of Q, okay, they say is going to be C5H11X. They say straight chain, okay, no branching. Where X is halogen, okay, bromine, chlorine, and iodine. Okay, the test is carried out. Okay, so if you want to find out the test, I think if you want to find out what kind of halogen, I think this one you should know by now. Yeah. So what you do, you just add with sodium hydroxide, warm. Then after that, you add dilute nitric acid. Okay, then followed by few drops of silver nitrate, and then you will see for whether there is any precipitate. So what we are looking for that is actually we want the silver, okay, silver ion react with the halogen. So there are three possibilities over there. You might get silver chloride, silver bromide, silver iodide. And in chemistry, you need to know all the precipitates color. Okay, Nicole, Trisha, can you give me the precipitate color for silver chloride? Jody?
White.
Okay, this is white. Okay, silver bromide,
Cream, then yellow.
cream, and then yellow. Now, there is additional thing that I want to teach you also. Okay, do remember, very important, but in the past, they don't actually focus on this. But in this paper, they did focus, because if you want to further test, because white, cream, and yellow is quite difficult to distinguish in lab. Okay, so what we do, we add ammonia. Now, the ammonia that when we add, okay, it can be dilute. After that, we can actually test with concentrated. Now, what happens, okay, when you add ammonia, okay, silver chloride, okay, they dissolve, okay, in dilute ammonia, okay, they also dissolve in concentrated ammonia. Silver bromide, okay, they don't dissolve or partially dissolve in dilute ammonia. Okay, but when you react with concentrated ammonia, they dissolve. For silver iodide, okay, both of them, even concentrated, okay, they are not going to be dissolved. So why this one is important, you can see in this particular question, okay, here, they say suggest the identity of X. Okay, I know it's cream precipitate, so it must be Br. Write an ionic equation. I think I told you how to actually write the ionic equation. If you are not sure, you can see the video about how do we cancel the spectator ion and so on. But by now, when you have a particular solid, you should be able to write the ionic equation easily. So if you have Ag plus, Br minus, so AgBr, please include the states, yeah, aqueous and solid. Now, describe further test. Okay, this is the part that I told you they ask. Okay, this is last time they don't ask, but now they ask again. Okay, so what do? Okay, we add aqueous ammonia. Okay, do remember you must mention aqueous ammonia. Okay, means with water. Okay, so add aqueous ammonia. Expected result, if it is going to be cream precipitate, it means we expect that when you add with dilute ammonia, the precipitate don't dissolve. Okay, so I put it as partially dissolved. Okay, so I know I can see some sort of it is dissolving lightly. So what I do, I actually try with concentrated. Okay, when I try with concentrated ammonia, completely dissolved, so I can conclude, okay, that this is going to be bromine. Yeah, contains bromine halogen. Now, the reaction Q with NaOH tends to proceed with an SN2 mechanism. Now, when it comes to SN2 mechanism, please remember this is nucleophilic substitution. We have two types of nucleophilic substitution, SN1 and SN2, the mechanism. How to remember? Do remember bigger number, okay? Then it will actually go with the smaller number. Smaller number will go with the bigger number, okay? SN2, okay, we have primary halogenoalkane, secondary halogenoalkane, tertiary halogenoalkane. Ignore with secondary because secondary can undergo both SN1 or SN2. Okay, so the rate is almost the same. But if I want to identify tertiary halogenoalkane will follow which mechanism? Okay, so tertiary will follow with a smaller number. So tertiary will follow SN1. Okay, primary will follow SN2. Okay, please actually memorize this. Now, The moment you get that, okay, then you will know that if you have tertiary halogenoalkane, you are going to get something to do with carbocation. Tertiary carbocation and primary carbocation. Which one is more stable? Tertiary carbocation is more stable than primary carbocation. Okay, so tertiary is more stable. Okay, so they have tendency to form carbocation. Primary, they are not stable. Okay, so they will not form carbocation. They will form intermediate. Okay, Nicole, Trisha, are you there? Okay. She's there. So here, okay, so if you have SN1 and SN2, okay, so here they say they will follow SN2. It means we are looking for intermediate. Okay, we are looking for the intermediate. So now they say that, okay, suggest a structural formula for the straight chain. Now they say structural formula. They intentionally give a lot of space. If they want, they would have actually give you a line. They don't want to give you line. Okay, because they want you to identify what is structural formula. Structural formula, this, if you put everything like this, then it's going to be displayed formula. So if you want structural formula, all straight chain, so it's supposed to be like this. But when I name CH3, CH2, 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 repeated 4 times, CH3, CH2, 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 left with Br. So that is going to be your structural formula. Can I actually simplify? Okay, I will suggest don't do that. Okay, don't actually put CH2 for Br. I will not advise you to do that. Okay, please actually write the full. Yeah. Now, explain why the reaction tends to proceed via SN2 mechanism. Let's actually find out. Okay, this one. Okay, Charlton, can you tell me this halogenoalkane primary, secondary, or tertiary?
Primary.
Primary. Can you tell why?
Only bonded with one.
Yeah, the carbon, okay, the carbon, when you say only bonded with one, okay, we are referring to the carbon. Okay, the carbon bonded to the Br is only bonded to one R group. This one is H, this is H. Okay, so this is going to be primary. Okay, so here explain why the reaction tend to proceed with SN2. Now, if you actually proceed with SN1, okay, it means the production of carbocation. You see, if they go SN1, then they will actually need to form carbocation. If they form carbocation, they will form primary carbocation. Primary carbocation, they are not stable. Okay, they are not stable. Why? Okay, because okay, whenever you have the R group is actually alkyl groups. Now these alkyl groups, what they do, they have what we call as positive inductive effect. Okay, I have actually mentioned this in the previous lesson as well. Okay, this positive inductive effect, okay, they will actually try to donate the electron towards the carbocation, and they will try to actually reduce the positive charge, okay, of the carbocation. So they will actually try to make it more stable. In this case, having only one alkyl groups over here, okay, they are not going to have enough positive inductive effect to make that primary carbocation stable. So the primary carbocation is not stable. So we need to figure a way how to actually put it in this answer. Okay, so explain why, because you can say that, okay, this reaction, okay, or the molecule, okay, the molecule is a primary halogenoalkane. Okay, so if it is primary halogenoalkane, okay, they only have, okay, one alkyl group, okay, one alkyl group, and this one alkyl group will have less positive inductive effect towards the carbocation. Therefore, the primary carbocation is not stable. So intermediate is formed instead. If you want to actually know about the mechanism of the reaction, okay, or how more about the SN1 and SN2, refer to my video. Yeah. So two different halogenoalkanes P and R, both with the formula, okay, C4H9Cl, are separately dissolved in ethanol, heated under reflux with sodium hydroxide. So this one, they are actually having alcoholic and then sodium hydroxide. Okay, so this one is going to be alcoholic sodium hydroxide. It means this one we are talking about elimination reaction. Okay, this one you go and check under halogenoalkanes. There are total 4 reactions. Okay, one is reaction with ammonia, reaction with NaOH, reaction with KCN, okay, in ethanol, ammonia also in ethanol, and then if you have NaOH in ethanol, then it's elimination. So total 4 reactions. So here, name the type of reaction happening. This is going to be elimination. Okay, what are we going to eliminate? Basically, we are going to eliminate the hydrogen and the halogen. So you will get out the HCl. Okay, you take out the HCl. Okay, let me actually reconnect again. Hold on. Okay, just wait for a while, guys. Okay, so you can see, okay, I was actually writing about this elimination. Okay, so elimination, so we have, okay, the H and Cl will come out. So we are going to actually have alkene, yeah, double bond will be formed. Now here they say write an equation using molecular formula represent the reaction occurring. I think they have given the molecular formula over here. So when you react with NaOH, okay, what do we expect? Okay, we have H and Cl going out. So the H will join with the OH to give you water. Okay, Cl will join with the Na to give you NaCl. Okay, left with, okay, the C4. Okay, so this one, if depending on where is the Cl, if the Cl is here, so H is here, so the double bond will actually form over there. So depends, okay, but whatever it is, methyl propene, okay, methyl propene, if I draw, okay, if I want to know what is this, okay, so it's going to be something like this. So you can count yourself, okay, C4H8, okay, so I have that, and I will see, I think it's already balanced, so I just leave it like that. Now, draw the skeletal formula of methyl propane. Okay, this one we learned today, the previous lesson, yeah. The new thing to actually write. Okay, but here in the marking key, they actually wrote like this. Okay, so it means carbon double bond C, carbon double bond C, and then there's C, C. So like this, like this. Okay, this one was given in the marking key. But I think we also learned the other day when we have the double bond, you can also write down, okay, in form of, if you want to show cis and trans, I think you can always show like double bond start like this. Okay, there is H and H, no need anything on the left hand side. There is CH3, so you write like this and then you write like this. If you give your answer like this, okay, this is also correct. Okay, so this one Gabriella Nicole was asking. So I think we try to see which one is the best. Okay, if you want to show cis and trans, okay, the best way to show, I think, is something like this. Yeah. In this case, give the name of P and R. Okay, the P and R. Okay, they say that chlorine. Okay, when you have C4, okay, and then you have this. So what? When you have this product. Okay, when you have this product. Okay, if I write this product over here, okay, I can actually say that the double bond is over here. It means that the H can come over here, Cl can come over here, or the Cl can come over here, H can come over here. Then only there is going to be double bond over there. So what I did was, I just put the H over here and then Cl over there. Okay, this one, what I did was maybe I just supposed to put the H over here, okay, and then Cl over here. So you will get something like this. Okay, there's two possibilities of a thing that will happen. where when they actually remove this, the double bond will come here. When they remove this, then the double bond will come here. Still the same thing. So what is this name of this molecule? This is going to be methyl propane. Okay, there's no need to put 2 methyl. Okay, because methyl cannot go anywhere at position number 1 or position number 3. They have to be in the middle. So no need to say 2 methyl propane. Okay, methyl propane is enough. This is methyl propane. So this one is going to be chlorine. Chlorine can come at 1, can come at 2. Okay, so I put 2. So 2 chloromethylpropane. In this case, okay, the chloro came at position number 1. Okay, why not position number 3? So we always look at the smallest number, okay, when we name. So it's going to be 1 chloromethylpropane. Okay, that's going to be the answer. The last one. Okay, 2 more minutes. I do not know how to finish this in 2 more minutes. Okay, anyway, okay, you see here, okay, we have, okay, ethane, and then reaction 1 is to change it into alcohol. The only way to change something into alcohol, okay, is by using this method here, 330, 60 ATM and phosphoric acid. And then, okay, this is what, when you draw back, I see it's going to be primary alcohol. Okay, this primary alcohol, okay, they actually change into a halogenoalkane. Okay, how do we actually change into a halogenoalkane? Okay, they just react with any RCl will do. Yeah, just react with RCl, you will get halogenoalkane. And then here, okay, when you have the primary alcohol, they change into aldehyde. I actually change it over here so that easier can see. So I will change it into aldehyde. Okay, so that one I know is actually oxidation. You can use potassium manganate, okay, acidified. Okay, but the difference is you cannot use reflux, because if you use reflux, they will change into carboxylic acid. So I don't want to use heated under reflux. So it must be written distill and then warm. Cannot be heated also. Okay, distill and warm. Okay, so that you get aldehyde. So you distill and collect immediately. So you don't change that aldehyde to become carboxylic acid. Now aldehyde after that, okay, this is carbonyl compound. Carbonyl compound, when they actually react with this KCN, okay, when they react with HCN, okay, they will give you the nitrile and the OH. I think this one you go and read about nucleophilic addition reaction. Okay, this one, even the previous sample past year paper also we have done this. They say that, okay, when you want to react with ACN, okay, the catalyst is NaCN. And in order to get ACN, we prepare by adding NaCN H2SO4 in situ. In situ means within the same reaction vessel. Okay, but sometimes we get confused. Okay, when do we use HCN? When we use KCN? Now KCN, okay, we use, okay, when you are dealing with halogenoalkane. When you are reacting halogenoalkane with KCN, then you get nitrile. Okay, so that KCN, okay, will come under the ethanolic condition. You react with ethanol, okay, and then KCN, then you get the nitrile. But when you want to react aldehyde and ketone, okay, do remember is HCN. It's not KCN. Yeah, that is one way to remember. Okay, so here what will happen when you have any aldehyde, this aldehyde, what happens, okay, when I have HCN, okay, this part will have H and then the CN will come over here. So H and CN, okay, you will get this. So this is what you have over here. Then after that, they heat with dilute acid. Now this is a hydrolysis reaction. Yeah. So when you have this nitrile, when you heat with the dilute acid, what happens? You are going to actually change it into carboxylic acid. So this part will change into carboxylic acid. So I have written, I took everything over here. Okay, I took everything over here. Then this part will change into carboxylic acid. Okay. Now once I actually put everything, I think there's another one. Okay, if you have halogenoalkane, how do you change halogenoalkane into amine? This is the part that just now I mentioned. Okay, if you want to change it into amine, okay, you need to actually react. Okay, you need to react with KCN. Okay, KCN, react with KCN in ethanol. You are going to get amine over there. So this one is going to be nucleophilic substitution. But do remember, I actually wrote something over here. These nitrile groups that you form, okay, there are two reactions. One, if you add with acid, okay, you can have carboxylic acid, the one that we have over here. There is another one also reaction where when you have nitrile, when you react with sodium and ethanol, you are going to get amine. Okay, so I've written over there as well. So this one comes from the carboxylic acid chapter. Okay, take note of this. Okay, so they didn't ask, but do remember you need sodium and ethanol. So now I think when you try to answer this question, I think it will be way faster. Reaction 1, what is the name of the mechanism? Now reaction 1, okay, it is going to be you are trying to add, okay, into the H and OH. The name of the mechanism is going to be, what is the mechanism over here? Nicole, Trisha. Mechanism involving carbon-carbon double bond. Hurry up, hurry up. You're muted, Nicole, Trisha. What happened? Okay, you're not answering. Okay, anyway, okay, this is going to be, okay, electrophilic addition. Okay, take note, okay, if you have, okay, carbon single bond, then it's going to be free radical substitution. Carbon double bond, electrophilic addition. If you have RH, it means halogenoalkane, or if you have alcohol, then nucleophilic substitution. Okay, and then if you have, okay, C double bond O, then we are talking about nucleophilic addition. The rest, okay, no need to actually know for now. I think that is actually under JC2. We have also learned about electrophilic substitution as well. Yeah, that is actually for benzene. Okay, but this one we focus on AS. Okay, name and region and condition, I think it's already there. Okay, so the region is going to be steam. Okay, and then you need phosphoric acid. They want name, yeah. So phosphoric acid. And then 330 degrees Celsius, 60 atm. Okay, so 60 atm, phosphoric acid, and everything is there. For number 2, okay, the name of the mechanism for the reaction number 2 is going to be, I think this one is an oxidation reaction. So potassium manganate, okay, and then distilled warm sulfuric acid. So you need to actually put the name here. Acidified potassium manganate 7 or acidified potassium dichromate 6, potassium manganate 7. Okay, acidified potassium manganate 7. So acid, maybe you can put H2SO4, sulfuric acid. But it's very important to say that we are not going to reflux, so it's going to be distilled and warm. Next is going to be number 6. Okay, number 6 is going to be, this one is going to be halogenoalkane. You are going to change it to amine. So this one you will react, okay, with KCN, okay, KCN with ethanol. Okay, so here is going to be nucleophilic substitution reaction. Yeah, nucleophilic substitution. Name of the region and condition. So that is going to be potassium cyanide. Okay, potassium cyanide, KCN in ethanol. Okay, potassium cyanide in ethanol. So this is going to actually explain about that. Yeah, potassium cyanide in ethanol. Now next, okay, the last one, almost towards the end. Okay, now complete the diagram to show the mechanism. Okay, this one is going to be the mechanism, which is going to be nucleophilic addition. Nucleophilic addition. So we need to actually have, okay, the lone pair of electron. You don't see any lone pair of electron. We need to put that. We need the relevant dipole and curly arrow. 3 things that you need to do. Okay, so what happens here? I think generally when you have, okay, oxygen. So the oxygen, the electron, they will go here. Okay. So you will have a partial negative charge. Okay, so this one negative, so it means there is going to be a lone pair of electron. Okay, lone pair of electron. So this one is going to be delta positive. Okay, this is going to be delta negative. So next, what's going to happen? This one will go here. Okay, so once it goes there, you will form the Cn. Okay, the double bond is broken. So if it is this negative, means the electron completely came over here. You need to show. Okay, once it came over there, okay, what's going to happen? Okay, here, okay, this electron, they will start to come over here because they need to actually form the delta negative, delta positive. Okay, next, this one will go to H. So you will get this. Once you get that, okay, this one will stay as additional Cn, and then they will continue react. Okay, so this one, initially when you use NaCN, okay, they are catalysts. It means we just require them a little bit in the beginning. After that, it will actually start to actually react, okay, with the HCN, okay, and then the reaction can continue. Okay, in the past, I think they have asked what is going to be the function of NaCN. The function of NaCN is to give the Cn minus immediately. Okay, once they give you the Cn minus immediately, the reaction can start. Okay, once it starts, then it will continue with HCN. Yeah. Now name the functional groups present in the product of reaction 3. Okay, product of reaction 3. So you have OH. Okay, I have OH, and then this is Cn. Okay, so you have alcohol group and nitrile group. Okay, I will finish in few minutes, sorry. Okay, so this one is going to be alcohol group and nitrile group. Draw the structure of organic molecule W formed in reaction 4. Okay, so in reaction 4, I have drawn over here. Okay, so we just need to draw. They didn't actually tell skeletal formula or any formula. They just draw. Okay, so we can actually just take the entire thing, we put it there. So maybe I'll draw nicely over here. Okay, so it means here carbon. Okay, carbon, hydrogen, CH3. So maybe let's say I stick to 1. Okay, I want to draw this plate formula. Okay, H, 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 C, double bond O, OH. Okay, so just double check and so on. I think everything will be correct. Yeah. So please, okay, I think we did this in yeah, I do not know. Okay, we tried to actually finish it, but we managed to finish it within 1 hour 15 minutes. Okay, but anyway, that actually includes explanation. Okay, so of course when you can calculate very fast. Okay, and then let's say you don't talk and you just do the paper like normal. Okay, roughly, okay, with explanation it takes about 1 hour 1 hour 10 minutes. Okay, so if without explanation, I think within 55 minutes, you should be able to do. Okay, that is actually the target that we are going to look for. Okay, so that is actually what we want to achieve. Yeah, so I'll stop recording now.